The research focuses on suppressing beam squint effect in near-field wideband communication systems using movable antennas. The authors propose a novel approach to maximize the minimum analog beamforming gain across the entire wideband spectrum by adjusting the movable antenna's positions. This is achieved by introducing a slack variable and adopting the smoothed-gradient-descent-ascent method. The problem is formulated as a max-min optimization, which is challenging due to non-convex constraints. To tackle this, the authors transform the problem into an equivalent form and leverage block coordinate descent and majorization minimization methodologies to construct concave lower bounds for the constraints. Numerical results verify the effectiveness of the proposed algorithms, demonstrating the benefit of utilizing movable antennas to mitigate beam squint effect in wideband systems. Here is a combined summary of the 2 pages. The authors propose a novel approach to optimize the antenna positions in a wideband multiple input single output (MISO) communication system aided by a massive array (MA) under the near-field (NF) channel model. The goal is to mitigate the beam squint effect, which degrades the system performance. To achieve this, the authors formulate a minimal array gain maximization criterion and develop 2 algorithms to configure the MA's positions. The first algorithm, Algorithm 1, introduces a slack variable to convexify the optimization problem. It iteratively updates the antenna positions using a second-order Taylor expansion of the objective function. The algorithm is summarized in Algorithm 1, which involves solving a convex optimization problem, P4, at each iteration. The second algorithm, Algorithm 2, is based on the stochastic gradient-descent-ascent (SGDA) method. It iteratively updates the antenna positions, frequency, and auxiliary variables using gradient ascent and descent updates. The algorithm is summarized in Algorithm 2, which involves solving a series of convex optimization problems, P5 and P6, at each iteration. The authors compare the convergence behaviors of both algorithms and show that Algorithm 2 exhibits faster convergence and a superior converged objective value compared to Algorithm 1. They also demonstrate the effectiveness of the proposed algorithms in mitigating the beam squint effect through numerical results. The authors provide detailed derivations of the gradient and Hessian of the objective function in Appendix A, which are used in both algorithms. They also discuss the complexity of the proposed algorithms and show that Algorithm 2 has much lower complexity and is more suitable for systems with large bandwidth. Here is the combined summary of pages 5 and 6. The convergence behaviors of Algorithm 1 and Algorithm 2 are presented in Figure 2, which demonstrates the objective function values versus the number of iterations. The array gain across the considered frequency band is shown in Figure 3, comparing the performance of Algorithm 1 and Algorithm 2 with m equals 16 and m equals 64. Figure 4 illustrates the average running time of one BCD iteration, highlighting the computational efficiency of the proposed algorithms. The Hessian matrix squared Tm, H, Tm, Fl, is derived in equation 24, which is a crucial component in the optimization process. The partial derivative squared H, Tm, Fl, partial differential y squared m, squared H, Tm, Fl, partial differential ym partial differential zm, and squared H, Tm, Fl, partial differential z squared m are computed in equations 25, 28, respectively. These expressions are essential for calculating the gradient of the objective function. The calculation of the gradient nabla f, k, tm, alpha m, f, is outlined in equation 29, which involves the partial derivatives of the beamforming vector b, f, with respect to the frequency f. The mth element of partial differential b, f, partial differential f is given in equation 30, which is used to compute the gradient nabla f, k, tm, alpha m, f. The references provided at the end of page 5 include a range of studies on massive MIMO systems, movable antennas, and beamforming techniques. These works have contributed to the development of optimized algorithms for wireless communication systems. The optimization problem is formulated as a non-convex minimization problem, which can be solved using the single-loop smoothed-gradient-descent-ascent algorithm proposed in 12. This algorithm is efficient in handling non-convex concave min-max problems, making it suitable for the optimization problem at hand.